Okay, I'm going to talk about solutions and solubility. So solutions, hopefully you remember what a solution is, but it's just a homogeneous mixture. And so you're taking something and dissolving it into something else. So say we have a beaker of water and we put in some salt and mix it and then it dissolves. So it is just a homogeneous mixture. It's going to be composed of one or more solutes dissolved in a solvent. So it could just be one thing dissolved into a solvent, or two things, or three things. It just depends. We'll focus on simple solutions where there's one solute and one solvent, at least to get started. And so you also should know what we mean by the word dissolving. So that's when you dissolve something, the particles of that substance get completely surrounded by whatever the solvent molecules are. Um, and so it looks like it disappears when it dissolves, but it's not reacting or anything like that. It's just being surrounded individually. And so then you can't see the particles because they're split up. Okay. It's not huge clusters of these things like it was in the solid. And so you've got to remember the terminology solute, that is the dissolved substance. And also you should keep in mind that the solute can be a strong electrolyte, a weak electrolyte, or a non-electrolyte. And so it'll, they behave differently. So remember, a strong electrolyte breaks up into ions when it's put into solution. So for instance, if you have NaCl, that's a soluble salt, or you have HCl, that is a strong acid, or if you have sodium hydroxide, NaOH, that is a strong base. All of those things are strong electrolytes. So when you actually put them in water, it's no longer that substance, at least intact. It is ions. Okay, and so it splits into ions. And so that can create some complications when you're dealing with solutions. So sometimes you'll want to talk about the actual individual ions and how many ions there are instead of how much of that initial solute was put in. And so your concentrations can increase because you have things splitting up into multiple things. And so when these things dissolve and break up into ions, instead of the original particles that you put in, so the NaCl or the HCl or the NaOH getting surrounded by water, the individual ions would. So like in the case of NaCl, it breaks up into Na plus and Cl minus, and the individual Na pluses get surrounded by water, and the individual Cl minuses get surrounded by water. Okay. And so the other component of our solution, remember, is the solvent. That is the thing doing the dissolving. Now, most often in intro and gen chem, when we're talking about solutions, we're usually talking about an aqueous solution. And so a solution where water is the solvent. If you're not told what the solvent is directly, you should assume it's water. Okay, because a lot of times we don't explicitly say that, because it's assumed that if we have a solution of sodium chloride, that it's in water, or if we have, acetic acid, it's in water, or if I have hydrochloric acid, it's in water, and so on. And so you've got to realize what we mean when we talk about a solution. If we don't specify the solvent, then it's in water. Although you can make solutions in different solvents. But most useful to us usually is in water. Okay, so in terms of the solutes, as I was saying, they can be electrolytes. They can be either strong, weak, or non-electrolytes. So you've got to remember what that means. because sometimes that'll change how you write things out or how you communicate things about that solution. So just as a reminder, strong electrolytes, they completely break into ions when they're dissolved in water. And so those things, since they completely break into ions, there's lots of ions in solution, meaning that solution will then conduct electricity very well. That is going to be anytime you have a soluble salt, a strong acid, or a strong base in solution. Whereas weak electrolytes, they partially separate into ions in solution. Okay, so a small portion of them breaks into ions. A lot of them stay kind of intact in the neutral form. But since there's a few ions, it does conduct electricity at least a little bit. That would include any insoluble salt that we put in solution, any weak acid or weak base that we put into solution. Okay. Now the insoluble salts, I know we use that term insoluble, indicating that it does not dissolve. And so it appears when you put that solid into water that nothing happened, but there is a small portion of it that does dissolve. And so you do end up getting some ions. And so it does end up being a weak electrolyte. And then we have our non-electrolytes. Those are the things that stay intact when dissolved. So they still get surrounded by the water molecules. Okay, so they still get dissolved, but they're not splitting into ions first. And so what you put in is what's still there exactly. It's just surrounded by the solvent particles. And since it doesn't split up into ions, there's no charge in that solution to help carry the electrons. And so it doesn't conduct electricity. That would include any neutral molecular compounds. And when I use that term neutral, I'm not really saying no charge. I'm saying neutral in the sense of it's not an acid and it's not a base. Okay, because some molecular compounds are acids and some are bases. And so I can't just say molecular compounds. You got to be careful with that. Okay, now let's talk about solubility. So solubility is the maximum amount of something that can dissolve into some solvent. Okay, so if we're talking about the actual solubility, that has a number associated with it. Okay, so there is a measured amount that you can determine, you know, of something that will dissolve in a particular solvent. So most of the time we're talking about ionic compounds in water. Okay, although you can talk about the solubility of all kinds of compounds in all kinds of solvents, if we focus on ionic compounds in water, usually you can look up those solubility values, and typically they're tabulated as how many grams of an ionic compound will dissolve in 100 milliliters of water. Okay, and so it'll have a unit of grams of this per 100 mils of water. But it can be reported a little differently. You just have to pay attention to the unit given. Sometimes instead of grams per 100 mils of water, it'll be given in milligrams per 100 mils of water, if not very much dissolves. And so it does tell you, excuse me, it does tell you how much could dissolve in a given amount of the solvent, okay? Now, when we're talking about solids being dissolved into a liquid, we typically use the terminology soluble and insoluble. So soluble would indicate that that solid does dissolve into the liquid, whereas insoluble would indicate that it does not dissolve in the liquid or very little dissolves. Okay, so insoluble, sometimes people will call it slightly soluble. So a little bit dissolves, but not a lot. And when we're talking about a solid dissolving in a liquid, like I said, a lot of times we're talking about ionic compounds. And so it's useful to have on hand some solubility rules when you're dealing with solutions of ionic compounds, because that will help you determine, is this substance soluble or not soluble? Okay, so this table is the same table that I've went through when we were looking at precipitation reactions. And so you just look up the ions in the compound and figure out, is it soluble or not, based on the rules given here. But we're not always looking at solutions of some solid being dissolved in a liquid. We could also be dealing with a liquid dissolved in a liquid, okay? And if that were the case, they typically switch up the terminology. Instead of saying soluble and insoluble, we'll use the terminology of miscible and immiscible. Okay, so if the two liquids actually dissolve or mix, then we say that they're miscible. But you could, I guess, say that they're soluble. It's just not really the proper term. Whereas immiscible would mean that they don't mix. And so that's when you mix two liquids and you can shake it all you want, but eventually it splits into two layers. Those are immiscible liquids, which again, you can kind of call it insoluble, but the immiscible is the proper term. Solubility, generally, if you're truly talking about solubility, you are given a numeric value, but the terminology given here, the soluble, insoluble, miscible, immiscible, that's more of a generic way to talk about solubility, because that's just a 50-50 saying it either dissolves or it doesn't. Whereas when we say that things don't dissolve or they don't mix, it's not 100% true, because there's always a very small portion at least that does. So using the term insoluble or immiscible doesn't mean that 0% of that solute mixed or dissolved, because there's always a little portion of it at least. Okay, now let's talk a little bit about the factors that affect solubility. Ooh, I don't think I drank enough coffee this morning. So now I'm going to focus on having a liquid solvent, but we'll look at different phases of solutes and talk about what factors would affect their solubility. Okay, because sometimes you can change things to get more of something to dissolve or to get something to precipitate out or undissolve, I guess you could say. And so if we think about solid solutes, this is by far our most common types of solutions that we would be dealing with in intro and general chemistry, is putting a solid into a liquid and dissolving it. And this, you need to know, is highly dependent on temperature. Okay, so if you change the temperature of your solution or of your solvent, then more or less solute might dissolve. Now, in general, when you increase the temperature, the solubility increases, okay? So that's because really as you increase temperature, there's more kinetic energy, so there's more motions, and so it can more easily break apart the intermolecular forces between the solute particles and surround them. And so in general, for most solids, the solubility is going to increase with increasing temperature. Okay, and it isn't 100% true, so that's why I say generally. There are some solids that it's the opposite trend, where increasing temperature actually decreases solubility. That's a little bit more unusual. You should generally assume that it's going to hold true. Increasing temperature increases solubility. So if you try to dissolve some solid and some of it dissolves but not all of it, you could always heat up the solution, and generally that will help dissolve the rest. Now, if you have liquid solutes, they really follow the like dissolves like rule. Okay, it's pretty much, that's what it is, and that's that. You can't really change it. And so the like dissolves like rule basically tells us that similar things will mix. Okay, so polar solutes or polar solvents will dissolve polar solutes and ionic solutes. Okay, so polar things have dipoles. So they have these permanent dipoles. And so they want to interact with another permanent dipole or a permanent charge. And so polar solvents that have this dipole will interact with polar solutes that have a permanent dipole as well, or with ionic compounds, because ionic compounds are composed of actual full charged ions. And so those are things that like to interact with one another because they want to interact with the other charges. Because when the negatives of one thing interact with the positives of the other, whether they're partials or full charges, it doesn't matter. It's still favorable. Whereas nonpolar solvents are going to want to interact with other nonpolar things, so nonpolar solutes. Okay, and that's because they only have temporary dipoles, from their London dispersion forces. And so those temporary dipoles, since they're only there for very short instances, they don't want to interact with things that have charges all the time. Okay, so nonpolar things mix with nonpolar. Now, we can also talk about gas solutes. And so if we are dissolving a gas into a liquid, that actually is going to be affected by both temperature and pressure. So we can manipulate the solubility of a gas by changing temperature or pressure or both. Okay, whereas remember solids, you can only change their solubility by changing the temperature. Okay, and liquids, you really can't do anything about it. It's either soluble or not. So the effect of temperature is that if we increase the temperature, the solubility of the gas actually decreases. And that's because, again, increasing the temperature increases the kinetic energy. So everything in that solution is moving faster. And so what happens is the dissolved gases, they move around faster and they're eventually going to get to the surface. And if they're moving faster, they're going to get to the surface quicker and then escape. And so that's why your solubility goes down with increasing temperature for gases. So that's exactly the opposite of solids. Okay, solids will dissolve more at increased temperature and gases will dissolve less. They'll actually escape. Whereas for a gas, if you increase the pressure, it would increase the solubility of that gas. When I say increase the pressure, I mean increase the pressure of that gas above the liquid. And so if this is in a closed container, we have this liquid, and then we pump in some more of the gas that we want to dissolve. And so we increase the pressure of it. We have more of those gas particles above the liquid, then more will get captured by the liquid. And so the solubility goes up. Okay. Now let's talk about one last thing, solution saturation. And so this does relate to solubility. So it's basically your relationship between solubility and your actual solution, okay, what you really have dissolved. So solubility is the maximum you could dissolve, and saturation is telling us, or the solution saturation is telling us, how much do we have relative to the solubility of this substance. So if we classify a solution as an unsaturated solution, that is a solution that has less than the maximum amount dissolved, meaning you could potentially dissolve more solute in that solution, okay, because it has room to take on more. Whereas we could also have a saturated solution. A saturated solution has the maximum dissolved. So the solubility is how much is dissolved in there. And so for that, you can't add, or you can't dissolve more solute. You can add all the solute you want to that solution. It doesn't mean it's going to dissolve. So if you had a solution and you didn't know if it was unsaturated or saturated, you could add more solute. And if that solute dissolves, then you had an unsaturated solution. But if it doesn't, then you had a saturated solution and still do. Um, Now, you can also have a super saturated solution, um, which I think I spelled that as two words, but it's usually one. That's okay. A supersaturated solution has more than the maximum amount of solute dissolved. This is an unusual scenario. This isn't something that you can create easily. You can't just put more solute in and magically get it to dissolve past the solubility. You actually have to do it by manipulating the temperature. So you increase the temperature, get more stuff to dissolve, then you carefully cool it down, and then you have a supersaturated solution. And so when you have this solution, it isn't stable. Okay, so any disturbance of that solution will cause the extra solute to come out of solution, including if you tried to add more solute. If you started adding more solute and it was already supersaturated, immediately the rest of the stuff would precipitate out. And so a supersaturated solution is a special case. The solutions we would deal with in this class would always be either unsaturated or saturated. Supersaturated, if we wanted to talk about one, it would be very clear that first this solution was heated, all this stuff was dissolved, and then cooled down. So we don't typically deal with them because they're trickier to make, and since they're so unstable, you're not going to keep it super saturated for very long. Okay. Okay. So that is the basics of, solutions and solubility.